Okay, if you would go to your terms of reference and look at model building stage 2, this is where we are now. We're just going to set those initial boundary conditions. It's a very short lesson that I want to show you, but it's really important, and there are going to be some little tricks that are involved over here. So if we go back to our spreadsheets, we've set things up as they are. But now I have set up the Streeter-Phelps model, and I put a little green coloring into that first line of the model to remind myself that these are the initial boundary conditions, and that the formulae in our second row are not necessarily going to be the same as the formulae in the first row. So they're boundary conditions, they're where the mixing point occurs at time is equal to 0. I have, just for my own edification and remembrance, gone ahead and put down these labels so that I can remember C equals oxygen, D equals saturated oxygen less the actual oxygen, DO, and then L being the total load, and I'm calling it UOD rather than just carbonaceous load. So that's more or less where we are. And so let's first have a look at that. And then, of course, I've made these columns because these are part of the columns in that model building process. So you may want that model next to you, or at least that PowerPoint next to you as you start to look at this process. Okay, the first thing we do, we want to look at the remaining UOD at time equals 0. And to do that, we're really going to look at a couple of things. First of all, our UOD, we're going to have to add the UOD in the river and then add it to the UOD in the wastewater treatment plant. So we just multiply the concentration in the river by the flow in the river, multiply the concentration in the wastewater treatment plant by the flow in the treatment plant, and then divide by the total flow. So you may want to use a basis of 1 second or 1 day. It doesn't matter as long as you keep your time basis the same, because at the end of the day we're going to come out with a concentration of grams per cubic meter, which has no time dimension. So let's go ahead and do that very quickly. So we're going to say our, I'm going to just open brackets here, our UOD in the stream times times our flow at the mixing point, and I'm just going to take 28 meters per second plus the UOD in the wastewater treatment plant, that's milligram per liter, times the flow. There we go. And we're going to put brackets around all of this to make sure that we don't mess up. And we're going to divide that by the total flow, which would be this plus this. So it's going to come out to be a UOD of 8.8 grams per cubic meter. And if you kind of look at this, grams per cubic meter is the same as milligram per liter. So whatever you want to do there. But if you look at it, you know, the majority of your flow is at 4 grams per cubic meter, and over here, your wastewater treatment plant, which has a discharge right now of about 20% of your river flow, that's at 40. So that kind of number seems to make sense. So if you use those numbers and you come up with that number, you know you're in good shape. We're going to do the same thing with dissolved oxygen. It's exactly the same principle. Over here, we're going to multiply DO times our flow plus DO from the wastewater treatment plant times our flow from the wastewater treatment plant, and divide all of that by the flow from the river plus the flow from the wastewater treatment plant. And if my brackets are 100%, yep, and it comes out to 5.87. So we know that we're in the right ballpark. This thing D now is really, really simple to calculate, but there's a little trick I want to show you. We go, our D is going to be equal to our current or our saturated DO. So we go down to this cell over here, we pick that up as equal to that minus our dissolved oxygen. Okay, and return. Yeah, there we go. And so that's 2. So we're in good shape. But one of the things as you drag and drop this thing down here is it goes crazy over here. So what are we missing? Well, let me show you something very, very important. Is G6 is a constant. Sorry, not G6, B36. Down here, my B36. So you don't have to have the same formula numbers as I am, but in this context, B36. If you want that formula to keep that cell invariable all the time, the row and column the same, put a $sign in front of the B and a $sign in front of the 36. And if I drag and drop now, what you'll find is that although this formula changes, it goes from G7, then G8, G9, the B36 in the formula bar stays identical. And you've got to do that because you're referring to a constant. So we call that anchoring. You can put a sign in front of the row or column to keep it stable or constant, or you can hit the F4 button in your PCs. I'm on a Mac, so I haven't really found that command yet. Excel and a Mac for me is still frustrating. Okay, so we're in good shape now. Now we go on to look at that Streeter-Phelps term of KDL. So now we know what our KD is because we've already calculated it, but we want to make sure it's the right one. It's KD times in the delta time step formula. And so in this case, we go, it's going to be equal KD delta T. Okay, so it's that one. And while we're about it, let's go ahead and anchor those values. I'm going to just put a $sign here, put a $sign there. Now we know that's not going to change, times our load, or L. And there you go. You've got a number there. And KR, reaeration rate, times our D, our delta. Remember, D is that driving force that we have for reaeration. So we're going to multiply, here's our reaeration coefficient, and we're going to go ahead and just anchor that, put a $sign in front of each one of those, in front of the B and the 45, and then multiply by D. Now you've basically got your initial boundary conditions there. We're not going to worry about SOD and UOD yet. We're going to just look at that very straight Streeter-Phelps model. But once we've got that taken care of, we can start looking at refining it. Because I wanted to sort of take you through a couple of the things, some of the limitations of that basic Streeter-Phelps model, and then sort of some of the Klug bootstrap methods that come out. One last thing that I might add is that as you go through this, you may very well find that I've made mistakes. So if you do find that, let me know. Don't let it kill you. Don't let it perplex you. Let me know, and we can make sure to correct those. Guys, thanks very much. That's the end of our second part of the model building phase. Hopefully it hasn't been too confusing for you. And wish you all the best as you work in this, and as little frustration as possible. All right.